Welcome to Black Holes Explained, an overview of one of the most exotic, mind-boggling subjects imaginable, and one of the hottest topics in astrophysics. I think many astronomers and physicists agree with the great science fiction writer Isaac Asimov, who wrote the following in 1977 in The Collapsing Universe. Since 1960, the universe has taken on a wholly new face. It has become more exciting, more mysterious, more violent, and more extreme as our knowledge concerning it has suddenly expanded. And the most exciting, most mysterious, most violent, and most extreme phenomenon of all has the simplest, plainest, calmest, and mildest name: nothing more than a black hole. Well, far from being figments of the fertile imaginations of physicists and science fiction writers, these amazing objects are real. Nearly everyone has heard of them, but few people understand what they are, perhaps beyond knowing that they are regions of intense gravity trapping anything that is within them. Now, before diving into the subject of black holes, let me tell you a little bit about myself and the rationale for this course. I'm a professor of astronomy at the University of California, Berkeley, where I've taught an introductory astronomy course every year since 1987. One topic about which students always have loads of questions, both before and after taking my course, is black holes. Well, that's great, because a lot of my own research has been about black holes, and I think they're super interesting. I even conduct an optional 3 to 4 hour evening discussion of black holes where I present additional material and answer students' numerous questions about them. Also, the topic of black holes in an introductory astronomy course, including the one I did for the teaching company called Understanding the Universe, is normally spread across different topics. Black holes come up when we discuss stars, but also when we talk about galaxies, general relativity, and even particle physics. So this course is a great opportunity to bring together and extend the coverage of black holes that is typically spread across much, much more material. Black holes are among the most dense, most long-lived, most energetic, and maybe even the most information-rich objects in the universe. I think it's terrific to take 6 hours to gather together what we know about them and present it to you. But a word of warning. Many aspects of black holes are highly abstract and counterintuitive. You might want to view these lectures several times, or just focus on the main points. I will include very little mathematics, only enough to convey the essential points. Now let me start by pointing out that black holes seem to be all over the place in pop culture. For example, I've seen them in a number of cartoons. Some of these refer to public services such as healthcare or to other supposedly wasteful actions. There's a black hole here somewhere, Medicare gold, you know. I'm afraid there's a black hole in the finance department. All these people are being sucked in and stuff. You know, you've heard the saying, the frequent saying, don't let it go down a black hole. This often refers to money, specifically government funds, just cash zipping down into a black hole. Well, as President Obama early in his time as president said, I am not going to simply put taxpayer money into a black hole where you are not going to see the results. He knew that people would know what he meant, because generally people know that black holes suck things in. Black holes just swallow stuff in their surroundings. There was even a cartoon in 1892 that showed President Harrison disposing down a black hole the budget surplus left over by former President Cleveland. Here's a sports cartoon where a black hole, is known to attract matter, and my research shows there's something known as a green hole that repels it. Golfers will like that one. Even very young children have heard of black holes. There's lots of kids' cartoons, and in fact, here's one drawn by a girl who had, these two aliens near a black hole, and she marks the black hole with certain doom, and, the aliens themselves are doomed. Even children have heard about them. Well, gosh, it's hardly a surprise. Black holes appear in pop music. Soundgarden has Black Hole Sun, and Muse played Supermassive Black Hole. Of course, There are many nonfiction books about black holes, serious books, and some are designed to arouse the curiosity of children and inspire them to pursue science. I think this is great. An old one that I know of is Journey to a Black Hole, an adventure in scientific discovery. It's great. It brings the kids in. Well, of course, in fiction, there are many cases of black holes, mentioned in popular books and novels. But in fact, some of them have little, if anything, to do with black holes. Perhaps they just use black holes, the phrase black holes, to draw people in. You could say that black holes are a very attractive topic. Well, Charles Burns, for example, created a wonderful series of comic books entitled Black Hole, which were later combined into a graphic novel of the same title. From what I can tell, it really has very little to do with black holes. It's really just about some teenagers in Seattle who were exposed to a horrible plague that turned them into zombies and had other weird effects on them, Well, of course, black holes very frequently appear in science fiction books and movies and in Star Trek and other TV series like Futurama. One of the best-known early examples was the popular 1979 Disney movie, The Black Hole. A lost spaceship, the USS Cygnus, is hovering just outside a black hole with a crew of faceless robots led by a human commander who is a scientist, during the main part of the trip. So anyway, here's a poster of it. A journey that begins where everything ends, and you see the stuff swirling down into the black hole. Internet jargon also features black holes. Specifically, black holes in the internet are sites where traffic won't route. There's a path between two computers. It exists, but messages simply get lost along the way. And in fact, there's a project called the Hubble Internet Audit to discover and monitor these black holes in the internet. A map is produced that enables users to monitor such black holes worldwide, or simply to check whether a given network address is active. And in the map shown here, you can see that at that particular time, there were a lot of internet black holes in the Northeast and in eastern Texas and Louisiana, and quite a few in Europe as well. So speaking of the internet, by the way, if you Google black hole in quotes, you'll get over 16 million hits. The first few are really very useful sources of information. And in fact, there are many, many other really great sources of info out on the internet. Of course, some are not so good, so you should check your sources. There's even some websites and ads that refer to black holes, but really have nothing to do with them. I once saw an ad that said, "Black hole, prices slashed, today only, free UPS shipping," as though you're buying black holes, but really it had nothing to do with black holes. Okay, so what is a black hole? What's the basic idea? Well, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. So, it would appear black. Now, I've long been offering my original prize-winning image of a black hole for only $10,000. Here it is. But, unfortunately, there does seem to have been a trend of people making their own versions of this black hole image with PowerPoint or Keynote or whatever. It's really not very hard to do. You just choose a black background. Well, why are black holes important? Well, they have extreme conditions not reproduced in any terrestrial laboratories so far. Black holes allow us to extend our study of the laws of physics, and they're exciting objects. We will see later that they are voracious eaters of material in their immediate vicinity. Even a decade ago, a president of the United States thought that they were interesting. William Jefferson Clinton, in his Science and Technology Policy Address on the 21st of January 2000 said, "There are so many more questions yet to be answered, and so I wonder, are we alone in the universe? What causes gamma ray bursts? What's in those black holes anyway?" President Clinton, curious about black holes. Well, where do black holes form? Beginning in the early 1970s, there was growing evidence that some types of massive stars might collapse to form black holes. Indeed, the gamma ray bursts to which President Clinton referred are thought to be produced by black holes. They're the collapse of massive stars producing a black hole in the process, and a burst of gamma ray radiation. And since the 1990s, there has been even better evidence that galaxies, including our own Milky Way galaxy, have these giant black holes at their center. We call them supermassive black holes. They have millions or even billions of times the mass of our own sun. Why should the object be black if it's collapsed to a highly compressed state? Well, no light is emitted or reflected. Okay? It doesn't emit any light, doesn't reflect any light, doesn't transmit any light. It's just black. Nothing comes out. Let's consider a plausibility argument based on Newtonian physics. Let me toss this apple up. Can't really talk about gravity without using the proverbial Newtonian apple, right? I never do it. Always have my apple with me. If I toss the apple up, it comes back down because of the mutual gravitational attraction between the Earth and the apple. If I toss it faster, it goes up higher before coming back down. So I could imagine tossing this apple at such a high speed that in fact it goes very, very far from the Earth and then comes back down. Now, if I had eaten my Wheaties this morning, I could in principle throw it at such a high speed that it would escape. It would never come back down. That's a speed known as the escape velocity. Happens to be about 7 miles per second here at the surface of the Earth, 11 kilometers per second. But now let's suppose we compress the Earth to half of its current diameter, and I throw the apple once again. The gravitational force between the Earth and the apple will have increased in this squished Earth, because now the apple is closer to the center of the Earth, and the gravitational force between two objects is proportional to the product of their masses, apple and Earth, for example, and inversely proportional to the square of the distance between their centers. So if I squish the Earth down to half of its current radius, the force of gravity will be 4 times stronger, because it's only half the radius, and 1/2 squared is 1/4, 1 over 1/4 is 4. So it'll take more effort, more energy for me to throw this apple at the escape velocity. Now let me squish the Earth down even more, to another half of its radius. The force of gravity will have grown yet again by a factor of 4, and I'll have to throw this apple, heave it, even faster to get it to escape. Not 4 times as fast, it's some other formula, it doesn't matter, but the principle is I have to throw it harder, heave it faster to get it to escape. Well, if matter is compressed so much that the escape velocity becomes the speed of light, we have an object that doesn't emit any light at all. Applied to a star, this would be a dark star, a star that doesn't emit any electromagnetic radiation, any photons. Can't see them. Essentially, this argument was used for stars in the late 18th century by the geologist and natural philosopher John Michell. In 1783, he wrote a letter about such dark stars to physicist and chemist Henry Cavendish, who brought it to the attention of others. Now, it was already known from astronomical observations that light travels at a finite speed, not infinitely fast. And at that time, Newton and many other physicists thought that light consisted of particles, the corpuscular theory of light. So gravity, in that case, could and should affect light much as it does apples. All right. Well, in 1796, the French mathematician and astronomer Pierre-Simon Laplace independently came to this same conclusion, Michell's conclusion. He wrote in his System of the World, a luminous star of the same density as the Earth, the same mass per unit volume, and whose diameter should be 250 times larger than that of the Sun, would not, in consequence of its attraction, allow any of its rays to arrive at us. It is therefore possible that the largest luminous bodies in the universe may, through this cause, be invisible. That was, Laplace having the same thought as Michell. Now, in the 19th century, the view of light as consisting of particles subsided. Instead, James Clerk Maxwell's wave formulation became the favored one. Now, waves were not so obviously affected by gravity, so the idea that there could be these dark stars from which light can't escape was largely forgotten. Indeed, Laplace himself apparently dropped mention of the invisible star in later editions of his book. The idea that some stars could be dark was revived in 1916 by the German physicist Karl Schwarzschild, shortly after hearing about general relativity from his friend Albert Einstein. He figured it out that there could be these dark stars and sent his solution to Einstein, unfortunately just before dying on the Russian front during World War I. Now, Einstein thought this was just an interesting mathematical conclusion. He didn't believe black holes actually exist. He basically thought there was no reason stars would ever collapse so much as to form them. Might be possible in principle, but that simply doesn't happen in practice. And apparently, even Karl Schwarzschild himself was skeptical about the physical reality of black holes. Nevertheless, following Schwarzschild's mathematical formalism, one can show that if you compress material to a radius that's at least as small or smaller than twice its mass times g, Newton's constant of gravity, divided by the square of the speed of light, 2gm over c squared, in that case, the escape velocity reaches or exceeds the speed of light, and so in principle, the object will appear dark. So the radius of a black hole is directly proportional to the mass of the black hole. The more stuff you have, the bigger is the radius into which you have to cram it before it becomes a black hole. So high-mass black holes are physically bigger than low-mass black holes. It's interesting that the Newtonian argument fortuitously gives the same formula, though we do really need Einstein's general theory of relativity, since light doesn't have mass and shouldn't be affected by Newtonian gravity. The radius of the black hole, the Schwarzschild radius as it's called, marks the boundary. Curiously, Schwarzschild in German means black shield. And indeed, one cannot see beyond that radius. You know, it's like a shield. But this is probably not what motivated Karl Schwarzschild to do his calculations. Black holes are generally quite small. If I had a star having, say, 10 times the mass of the sun, and I were to compress it to form a black hole, it would only be about 20 miles in radius, about 30 kilometers. So about the size of a large city like Los Angeles. On the other hand, there are supermassive black holes in galaxies that reach 1 billion solar masses, say. And such a black hole would have a Schwarzschild radius of about 3 billion kilometers. Now, that's roughly 20 times the distance of Earth from the Sun, 20 so-called astronomical units, roughly the orbital radius of Uranus in our solar system. So a giant black hole is, though much bigger than a small black hole, still only comparable to our solar system in size, yet has vastly more mass. If I were to compress Earth to a black hole, it would have a radius of about 1 centimeter, about like a walnut. If I were to compress a human to a black hole, you or me, now don't worry, I'm not going to do it, the radius would be 10 to the minus 23rd centimeters, which is 10 orders of magnitude smaller than a proton. Holy moly! You'd need about 10 billion people, more than Earth's population, to get a black hole even the size of a proton. Now, a proton is yay big, and I exaggerate greatly. So, it takes a lot of mass to make even a proton-sized black hole. They're pretty small. The set of points having a radius equal to the Schwarzschild radius is called the event horizon of a black hole. It's not a solid surface, like the surface of a sphere like this. Rather, it's like a one-way membrane. You can go in, but you're not going to get out. And in fact, the true significance of the event horizon wasn't understood until about 1958, when David Finkelstein, a physicist, studied the mathematics of black holes and realized really the significance of the event horizon. It's called an event horizon because simply you can't see events that occur beyond it. It's a horizon. Now, it would be a real event for you if you were to go beyond it. Bye-bye. You can go in, but you're never gonna get out. So let's quote Dante's Inferno. "Abandon hope, all ye who enter here." There really should be signs, warning signs near black holes. Do not enter, wrong way. Don't go any further, Buster, you're not going to get out. In fact, this is kind of like being in the Oakland Raiders black hole zone. The Oakland Raiders, an Oakland football team, has this zone where there are these rabid fans that call themselves, the black hole zone. And I think it's because if some other spectator happens to wander in casually, they will suck that spectator in and never let him or her out again. In that sense, it's a black hole. Now, there was a horror movie in 1997 called Event Horizon, but as far as I can tell, it really had nothing to do with black holes. Event Horizon was an explorer spaceship in the outer parts of the solar system, and it was invaded by some unspeakable evil around the year 2040. Here's a poster, infinite space, infinite terror. Well, again, they use Event Horizon, I think, and black holes to kind of draw people in. Despite the correct equation being given by the simple Newtonian argument, the only way to properly understand black holes is with Einstein's general theory of relativity. Basically, light is trapped inside a black hole because space and time are so severely warped within the event horizon that the light simply can't escape. Now, you can understand this warping a little bit if you take an elastic sheet and stretch it over a circular frame like this. If there's no mass within it, it looks flat. And in fact, ping pong balls roll along straight lines like that. But if I were to put this heavy ball in it, the thing bulges down, being pulled by the Earth's gravity. And now when I flick a ping pong ball, it goes in a circular orbit. In fact, it spirals in toward the mass, and that's because of the friction between the ball and the fabric. If there were no friction, it would just keep on going in a circular or an elliptical orbit forever. Now, this analogy is a bit unfair because I used the Earth's gravity to pull on the ball and to hence create an artificial gravity in this piece of, elastic. But, that's the way it goes with analogies. No analogy is perfect. Otherwise, it would be the very phenomenon you're trying to describe, and so it really wouldn't be an analogy. Now, as a star gets progressively smaller, progressively denser, its gravitational field, that is, this warping of space, gets stronger and stronger. Eventually, when the sides become vertical, you have an event horizon. So here's a graphical representation of this curvature of space, and it turns out of time as well, and a horizon forms. Light coming from a region close to, but outside that dense star, can get out. But it is bent unless it goes along a radial trajectory, and it is redshifted. It loses energy. So if you look at these light beams, they start out yellow, and as they go out, their wavelength becomes longer, redder. They are experiencing gravitational redshift because the light is losing energy trying to get out from within the vicinity of the black hole. If you compress the star even more, it turns out the light is bent and redshifted even more. And the bending is really interesting. If you shine the light in a direction perpendicular to that toward the middle of the collapsing star, you can get light orbiting around in what's called a photon sphere. It orbits around at a distance of 1.5 Schwarzschild radii from the center of the collapsing star. If you further collapse the star, the cone within which light can escape from the star gets narrower and narrower until finally, when the star collapses down to the Schwarzschild radius, the cone disappears entirely. You form a horizon. Surrounding it is a photon sphere where photons could orbit. If you were looking in one direction, you could perhaps see the back of your head, okay? But the horizon will have formed at this point, and nothing beyond the horizon would be able to get out. Light couldn't get out because the cone will have squished down. Light gets trapped by the extreme curvature of space. It really doesn't even go partly out of the hole the way an apple does. It just stays in all the time. It just can't even get partly beyond the horizon. The horizon doesn't let anything out whatsoever. Now, you can also say that, from one perspective, the light does get out, but it loses all of its energy through the gravitational redshift in trying to get out, so nothing is left. That's a different way of looking at it. If it lost all its energy, there's no photon left. There's no wave left. So here you see this gravitational redshifting occur. If you imagine the particle to be at the event horizon, those waves become longer and longer until finally the wavelength is infinitely long and the associated energy is zero. The star is dark, just like Mitchell and Laplace had said over a century before Karl Schwarzschild's amazing work. Now, the name black hole was coined by John Archibald Wheeler at Princeton University in 1967. And that's the name that stuck. It resonated with people. Dark star just didn't resonate as well. On the other hand, there was some initial resistance to the term because some people thought it sounded kind of naughty. But it prevailed, and that's what we call these things now, black holes. According to classical physics, matter inside the black hole continues collapsing to a mathematical point called a singularity, a finite mass in zero volume, a mathematical point, infinite density. Holy moly, is that possible? Probably not. Quantum mechanical effects almost certainly modify this conclusion. There is no such thing as a point-like particle. You cannot have all the matter concentrated into zero volume with infinite curvature of space and time. It's really hard to grasp the gravity of the situation. But the singularity may well be very small indeed, and surely has a very high density. So really that's the answer to former President Clinton's question regarding what's inside a black hole. A singularity, but we don't know really what it is in detail. We haven't figured it out yet. Now, to dispel a common misconception, let me say that black holes are not cosmic vacuum cleaners sucking up everything in space. You know, that's what some people think black holes are. They just will suck in everything in the universe, and if even a single black hole exists in the universe, Earth is in danger. No, 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 no. Far from the event horizon, space and time are normal. If the sun were to turn into a black hole, I hope it doesn't. You know, we would die, no heat, no light. There's no reason we think it will, you know, it won't. But if you were to somehow take a big cosmic vice and squeeze it down to a radius of 3 kilometers or less, it would turn into a black hole. But Earth's orbit would not be affected. Earth is 150 million kilometers away, 93 million miles. You know, whether the sun is the sun or a black hole makes no difference to Earth's orbit. The mass of the sun hasn't changed. The mass of the Earth hasn't changed. The distance between their centers hasn't changed. Nothing much has changed. You really must get quite close to a black hole in order to feel its special effects. It's easy to orbit a black hole from a safe distance. The Earth is in no danger, in part because, of course, the sun isn't going to turn into a black hole, and in part because there are very few other black holes in our immediate vicinity. Now, a non-rotating black hole is an idealization. It's an idealization because black holes, we think, form from the collapse of stars, and all stars are rotating to some degree. So, since rotation is conserved, a spinning object has to remain spinning, we expect real black holes to be spinning. Moreover, as real black holes accrete or swallow material from their surroundings, they will do so in a disk, and the rotational energy of that material goes into the black hole, causing it to rotate. The structure of a rotating black hole is considerably more complex than that of a non-rotating black hole. For a given mass, the event horizon is smaller, but still always spherical, like a spherical basketball, just as in the case of a non-rotating black hole. But if you look at this diagram, you can see that though the event horizon is smaller, there's this region around it called the ergosphere, where in fact no observer can remain stationary. If I were trapped there, no matter how I fire my thrusters, I would not be able to remain stationary. Space and time are dragged around the black hole so greatly that in fact nothing can remain stationary. The other interesting thing about a rotating black hole is that the singularity is a ring singularity, not a point-like particle. You could perhaps make it through in principle, but as we'll discuss later, it's in practice not possible. There are two horizons in a rotating black hole. If you start with a non-rotating one, there's one event horizon. With some rotation, you see that there's an inner event horizon and an outer one. There are two of them, plus the ring singularity. If you increase the rotation rate more, the inner one moves out, the outer one moves in. Eventually, at some maximum rotation rate, they merge and the horizons vanish, leaving a naked singularity, one not cloaked by a horizon. So you could stumble upon it with essentially no warning. Physicists don't think that naked singularities exist. Nature abhors a naked singularity, we think. So in fact, we think that this maximum rotation rate is never actually reached in practice. Otherwise, you'd get a naked singularity. Let me say one more thing about this dragging of space. In the most extreme form of a black hole, you have this ergosphere that whips around, dragging space around it, And if you were to view the black hole from the top, then a civilization could place itself near a rotating black hole, take garbage trucks into the ergosphere, dump the garbage at an appropriate time, and then emerge with more energy than those trucks had to begin with. If they then hit a little windmill or a garbage truck mill, they would cause it to spin, generate energy, solve their energy problem and their waste problem all in one blow. Now, this is quite impractical. It would require a pretty advanced civilization to achieve this, but it is nice fodder for science fiction books and movies. Well, having finished this brief introduction to black holes, we can begin to explore them in more detail. Black holes provide a very rich context in which to study the universe, with physical conditions difficult or in some cases impossible to reproduce in terrestrial laboratories. The structure of the course will be as follows. In lectures 2 and 3, I'll explain how black holes can be formed from the titanic explosions of dying massive stars. And in lecture 4, I will describe how astronomers actually find such stellar mass black holes. Now, there are also supermassive black holes in the centers of galaxies, and these will be the subject of lectures 5 and 6. I'll discuss also how we can, in principle, listen to merging black holes. Now, the possibility of travel into and through black holes, perhaps to other universes, will be the subject of lectures 8 and 9. And in lectures 10 and 11, I'll describe how, according to quantum physics, black holes might not be black after all, and perhaps the devoured information even escapes from them somehow. In the final lecture, I'll explain that the mini black holes that physicists hope to create in the Large Hadron Collider will provide important clues to a unified theory of physics and will pose, by the way, no danger whatsoever to Earth and its inhabitants. Be prepared to get exposed to some of the wildest, most provocative concepts you've ever heard. It's going to be one heck of a lot of fun.